In the previous video, we introduced the representation of floating point numbers. We now look at the algorithms used to perform the main arithmetic operations. We mainly focus on algorithms rather than floating point arithmetic units because a floating point unit is built from the same building blocks already introduced for integer arithmetic. These blocks are then appropriately controlled by additional circuitry according to the algorithms we are about to present. For the sake of brevity, we will not analyze such a control circuitry. Floating point operations are carried out under the following initial assumptions. The operands are in normalized form, and they do not represent special values. All the special exception cases require separate handling, which is beyond the scope of this lesson. We here examine the operations of addition, subtraction, multiplication, and division. However, these are first preceded by two supporting operations, normalization and rounding. Normalization is a transformation applied to the result of an arithmetic operation whenever the result is not normalized. If the mantissa is less than 1, normalization shifts it left until its first one becomes the implicit leading one. It then subtracts from the exponent an amount equal to the number of left shifts performed. A similar situation occurs in the opposite direction. If the integer part of the mantissa is greater than 1, the operation shifts the mantissa to the right until there is exactly one leading 1 on the left of the radix point and adds to the exponent the number of right shifts performed. The same procedure is also used to align operands when an arithmetic operation requires their exponents to match, thus resulting in one of the operands being in non-normalized form. During floating point operations, intermediate results often have mantissas with more bits than the available precision. This typically happens, for example, when addition produces a mantissa with an integer part greater than 1. In this case, the normalization right shift increases the number of fractional bits, causing the mantissa to exceed the available bit width. To handle this situation, we apply rounding. Rounding is used to remove the excess least significant bits of the mantissa, allowing the result to fit within the available number of bits. As a consequence, the result is no longer exact, but an approximate representation of the original value. The IEEE 754 standard defines several rounding methods that can be used for this purpose. The simplest one is truncation, where the excess least significant bits are simply discarded. The standard does not mandate a specific rounding method to be used in hardware. The choice of the rounding strategy is left to the implementation. Let us now look at the algorithms for the main arithmetic operations. The floating point addition-subtraction algorithm can be described through the following steps. Two normalized operands are provided as input. The exponents of the two operands are compared, and the operand with the smaller exponent is identified. The mantissa of the operand with the smaller exponent is shifted right by a number of bit positions equal to the difference between the two exponents in order to align the radix point between the mantissas. Indeed, we use the normalization procedure to align the operands. Moreover, during this operation, as well as any normalization step, least significant bits that exceed the available precision are truncated. The exponent of the result is assigned the larger of the two operand exponents. The algebraic addition or subtraction of the mantissas is computed using the standard algorithm for numbers encoded in sign and magnitude format, in order to determine both the value and the sign of the result. If needed, the resulting value is then normalized. We can observe that the main module of a floating point adder subtractor is the mantissa adder, but a significant amount of control logic is also required to determine which operand has the smaller exponent, to compute the required shift, to determine the sign of the result and the actual algebraic operation to be performed based on the signs of the two operands and the required operation, to check whether the result must be normalized and to perform the normalization. Let us now go through a complete example of floating point subtraction. For the sake of brevity, we will skip examples for the other operations. We want to compute A minus B, where the values of the two operands are shown here. First, we compare the exponents. Since the exponent of b is smaller than that of a, and their difference is equal to 2, we need to align the operands. To do this, we shift the mantissa of b to the right by 2 positions. In this way, both operands have the same exponent, which becomes the exponent of the result. Next, we consider the signs of the operands and the required operation. Since the two signs differ and the operation is a subtraction, the actual computation performed is the algebraic sum of the two mantissas. Moreover, the sign of the result is the same as the sign of A. Finally, since the mantissa has an integer part greater than 1, we normalize the result by shifting it to the right by 1 position and incrementing the exponent accordingly. This gives us the final normalized result. The second algorithm we examine is for floating point multiplication. This operation is carried out according to the steps listed below. As usual, normalized operands are provided as input. The exponent of the result is obtained by summing the exponents of the operands and then subtracting 127. Subtracting 127 is required when processing single precision floating point numbers because the exponents are encoded in excess 127 form. For double precision floating point numbers, it is necessary to subtract 1023. The mantissa of the result is computed by multiplying the mantissas of the operands. We use the standard multiplication algorithm for unsigned numbers, and the radix point is positioned so as to leave 46 bits to the right in single precision floating point numbers. For double precision, there are 104 bits to the right of the radix point. The sign of the result is determined using the usual multiplication rule. Operands with the same sign produce a positive result, while operands with different signs produce a negative result. Finally, the result is normalized, if necessary. From an implementation point of view, the floating point multiplication algorithm is simpler than floating point addition because it requires less control logic, even though it uses two main arithmetic modules: an integer adder-subtractor for the exponents and an unsigned integer multiplier for the mantissas. Finally, this is the algorithm for the floating point division. The input operands are received in normalized form. The exponent of the result is obtained by subtracting the exponent of the divisor from that of the dividend and then adding the bias. 127 for single precision and 1023 for double precision. The mantissa of the result is computed by dividing the mantissa of the dividend by the mantissa of the divisor. The sign of the result is determined according to the usual rule based on the signs of the operands. Finally, the result is normalized, if necessary. Just like in floating point multiplication, the floating point division algorithm requires little control logic, but it relies on two main arithmetic modules: an integer adder-subtractor for exponent processing and an unsigned integer divider for mantissa processing.